Today, ladies and gentlemen, we shall beef up the graphing of our trig functions. We're going to be looking at how to transform them using our transformations that we saw earlier in the year. If this doesn't look familiar to you, you might want to go back to the function transformation series of videos and take a look at those and review those concepts. But just to remind us of what these different letters mean, A tells us that there is a vertical stretch, and that the scale factor, I'm writing SF, abbreviating scale factor, is the absolute value of A. If A is less than 0, then there is also a vertical reflection across, which would reflect us this direction across the x-axis. An example of a function that we'd see with trigonometry might be y equals 2 sine of x. The b, if there's a number being multiplied inside the function, that's a horizontal stretch. Scale factor is 1 over absolute value of b. If b is less than 0, then horizontal reflection, which would be this direction, we're reflecting across the y-axis. An example of this type of function might be y equals sine of 2x. And then addition and subtraction tell us not about stretching but about translating, sliding. The h is a horizontal translation, and it's in the direction of the x, it's horizontal, and the amount that we translate is h. If h is positive, the equation would say x minus 2. For instance, y equals sine of x plus 3. This would have a translation of 3 units to the left because technically speaking, h is negative 3. What are we subtracting from the x? We're subtracting negative 3. And lastly, the k is a vertical translation by k units. Exactly what it says. So this would look like y equals, let's change it up, cosine of x plus 1. So everything outside of the trig function is a vertical transformation. Everything inside the trig function is horizontal. Keep that in mind as we proceed. So we want to sketch this graph of y equals 4 cosine x over 3. So let's discuss this in terms of our transformations and then our trigonometric terms. What does the 4 do? It's a vertical stretch, scale factor 4. That's going to affect the amplitude. Amplitude is 4. The over 3, that's a b value. B is 1/3. So the horizontal stretch is a scale factor of 3. So my period that was 2 pi is now 2 pi times 3, which is 6 pi. So let's back this up. In general, let's generalize these things. For y equals a sine or cosine bx, the absolute value of a is amplitude. The period can be found by taking 2 pi and dividing by b, doing the opposite of what it says. So here, if we take 2 pi and divide by 1/3, that gets us multiplying by 3, or a period of 6 pi. This stuff in the box, pretty darn important for graphing trig functions. So let's go ahead and graph this. We have the information that we need. So I'm going to draw my xy axes, And I'm going to graph this the same as I do any other trig function. I'm going to go 1, 2, 3, 4, and write my period, 6 pi. This would be 3 pi. This would be 3 pi over 2, 3 pi over 2, 6 pi over 2, 9 pi over 2. My amplitude is 4. So I'm going to go 1, 2, 3, 4 units up, 4 units down. And since I'm cosine, remember cosine does one of those. So I'm going to start out at my amplitude. At the end of my cycle, I'll be back at my maximum. Halfway through, I'm at my minimum. And at these other 2 points, I'm at my zeros. And once you know it, I have now graphed it from 0 to 6 pi, just like the problem asked me to. Write down the amplitude and period of the function. This should be one of the absolute first things that you do before you even attempt to graph this. Identify what the amplitude is, identify what the period is. Without them, it's very, very difficult to build this graph. Next example, sketch the graph of y equals sine x plus 2 for x is an element of 0 to 2 pi. There's my domain. I'm graphing from 0 to 2 pi. Is there an amplitude change? No, amplitude is 1. Period. Is there a b value? Are we multiplying the x by something? No, so the period is 2 pi over 1 if we want. Is this plus 2, is that with the x in parentheses, or is it on its own outside? I hope you're saying that's outside, which means there's a vertical shift of up 2 units. So here's what we're going to do. Let's get our axes drawn. And I'm going to put my vertical shift on here right away. And what I'm going to do is I'm going to mark up 2 units, and then I'm going to draw myself a dashed line. This becomes my new midline. This becomes my new x-axis, if you will. This is where my wave will be centered on. Now I'm going to scale my x-axis. 1, 2, 3, 4 marks. I write my period. I label the rest of them. And now my amplitude is going to be 1 unit. So I'm going to go up 1, that would put me at 3 from the midline, and down 1, which puts me at 1. This is the line y equals 2. And now I'm going to draw my sine curve from this line. So my sine curve starts on the midline. It goes up to its maximum. It goes back to the midline, down to its minimum, and ends a cycle on the midline. And I can draw my curve. And this problem has asked me to draw this curve for 0 to 2 pi, which I have just done. If it asked me to go to 4 pi, I'd go 1 cycle further. Find the maximum minimum. Well, the maximum value would be here. Its coordinates are pi over 2, comma 3. Our minimum value has the coordinates 3 pi over 2, comma 1. So the maximum value of the function is 3. The minimum value of the function is 1. And there we go. Sketch the graph of cosine x plus 30 degrees. So here we're graphing in degrees. How does that change things? All it changes is our scale. So let's put our axes down, and let's identify the important bits and pieces. Amplitude. Amplitude is 1. Period. 2 pi over b is, there's no b here, it's a 1, so period still is 2 pi. Is there a horizontal shift? Yes. The horizontal shift is going to be left 30 degrees. Is there a vertical shift? No. This plus 30 is inside the parentheses, so this graph behaves opposite of what we would expect, which is, since it says plus 30, we say it goes left 30. So let's scale our axis. 1, 2, 3, 4. That's 360. That's my period. And since I'm in degrees, I probably don't want to call the period 2 pi. I want to call it 360 degrees. So this would be 180. This would be 90. This would be 270. And anytime there's a horizontal shift, what I'm going to do is I'm going to graph this as if there wasn't one, but I'm not going to draw the curve, and then I'm going to move my points. So I'm going to draw these early points in red. These are unshifted points. Cosine would follow this. And if I were to graph it, there's my cosine. If the plus 30 wasn't there, but guess what, guys, it is. So how far do I have to move this? Well, I have to figure out how far 30 degrees is here. And it's 1/3 of the way from 0 to 90. So it's that little nugget right there. So I'm going to move all of my points back that far. So that point goes here. This point would go to there. This minimum would go back 30 degrees. This point goes back 30 degrees. This point goes back 30 degrees. And now I can draw my curve going through these points. And now it does say I want 0 to 360, so what happens here? Well, this actually comes down again like that. And what I would do, I would extend this out another 90 degrees, 360, 450 degrees. That's where it would hit 0 normally. That's where my red curve would hit. So my blue curve, my actual curve, goes 30 degrees back. I'm just going to extend my cycle so that I hit the requirements of going from 0 to 360. If you give a little bit extra on your graph, that's okay. You never want to fall short when you're given a specific domain. If you want it to be precise, you could come back and erase this part and say, I don't really care about that much. I'm going to erase that. So now state the minimum and maximum values of the function. Well, the maximum value is 1. The negative value is -1. And the values of x at which they occur. Well, this is 30 degrees before 0. But since I want to graph between 0 and 360, what I really care about is this one. That one's not in my domain. So it's 30 degrees before 360, so that is 330 degrees, comma 1. This one is 30 degrees before 180, so 150 degrees, comma, -1 for the minimum. And there's our graph. Isn't it beautiful, ladies and gentlemen? It's not so bad to graph these things. You do have to be careful with your scale on the x-axis. If you understand the scale on your x-axis, these problems are not very, very difficult to graph.